Now let's discuss how to solve logarithmic equations. The goals for this lesson is to use the definition of logarithm to solve logarithmic equations. And then we use the logarithm properties and the definition of logarithm to solve logarithmic equations. And then use the one-to-one property of logarithms to solve those equations. So we already have seen that every logarithmic equation, b a log of x base b equal to y, is equivalent to the exponential equation b to the y equal to x. So we can use this fact along with the rules of logarithm to solve for logarithmic equations where the argument is an algebraic expression. So as a general note, for any algebraic expression S and real numbers b, c, where b is greater than 0 and not equal to 1, the log of s base b equal to c can be written equivalently as b to the c equal to s, or log of s base b equal to c, if and only if b to the c is equal to s. For example, let us solve the given expression here. To do that, we first have to isolate the natural logarithm of x. And then we would use the definition of logarithms to write this in exponential form to get our value for x. So first, we have this equation or expression here equal to 8. So this is the given. To isolate ln x, we first have to transpose 4 on the other side. We can do that by subtracting 4 on both sides. So as you subtract 4 on both sides, 4 minus 4 is 0. That leaves you 2 ln x. And 8 minus 4 is equal to 4. Then after that, you divide both sides of the equation by 2. So you can cancel the 2 here, then you have ln x. So you have ln x equal to 4 over 2, which is equal to 2. Then you use the definition of logarithm. You know that ln x is just logarithm base e. So the base is e, the exponent is 2, and the number is x. So therefore, x is equal to e squared. So let's consider another example. Solve for 8 plus ln x equal to 12. Now to do this, let us isolate first ln x, or the natural logarithm of x, and then we use the definition of logarithms to write the logarithm in exponential form and get our value x. So first, let's consider the given here. We will transpose 8 on the other side of the equation. That is done by subtracting 8 on both sides. So you're left with ln x here. So 8 minus 8 is 0. That's why you only have ln x. And 12 minus 8 is equal to 4. Then from here, you use the definition of logarithm. Note that the natural logarithm ln is just the logarithm base e. So the base is e, the exponent is 4, and the number is x. X is equal to e to the 4th. Now sometimes the problem is more complicated, and in addition to using the definition of logarithms to solve an equation, we must also use the rules of logarithms. For example, let us consider the equation here, log of 2 base 2 plus log of 3x minus 5 base 2 equal to 3. Now to solve this equation, we can use rules of logarithm to write the left-hand side in compact form and then apply the definition of logarithm given by this, y equal to log of x base b. You could write this as b to the y. So this is just b to the y equal to x to solve for x. Now, so to write this in compact form, it is important to notice that we have a sum here. This is an expanded form, and we know that the logarithm of the product is equal to the sum of logarithms. So this actually came from log of m plus log of n. We can use different base b here. Oops. This is equal to log of mn base b. So that means that to write this in condensed form or compact form, this is just equal to log of the product of 2 and 3x minus 5. So 2 times 3x minus 5 and base 2. So log of the product base 2 equal to 3. Then we can proceed to simplify the product here and write it as 6x. So that is 2 times 3x is equal to 6x minus 2 times 5 here. That gives us negative 10. Or 2 times negative 5 is negative 10. So now this is the simplified form for the argument. So we have 6x minus 10 base 2. Then we can use the definition of logarithm. We can apply this definition here that logarithm of x base b equal to y is equivalent to b to the y equal to x. So the base here is 2. So if you look at this one, the base is 2. The exponent is 3. That's how you get 2 cubed, and equal to the given expression here, the algebraic expression. That is equal to 6x minus 10. So now we have here an equation, and then we should be able to solve for x. So expanding 2 cubed, we get 8 on the left-hand side equal to 6x minus 10. And we isolate x by adding 10 on both sides. So you have to add 10, and this cancels out if you add 10. And then if you add 10 here, that gives you 18. So 18 equal to 6x. And then after that, you divide both sides by 6 to get x. So therefore, x is equal to 3. So next, we will solve the given expression here, which we want to solve for x. So our first step is to combine these two expressions, write this in compact form. So since we have difference of logarithms here, it is important to take note or to remember that log of n or m over n base b is equal to log of m base b minus log of n base b. The logarithm of quotient is equal to the difference of logarithm. So with that, we can combine these two. So since we have minus, so we have difference of logarithms. So that is just the logarithm of quotient. So you could write that as logarithm of 5 divided by x plus 1. So logarithm base 3. And the right-hand side is 3. Then the next step is to write this in exponential form. This is going to be our base, and this is the exponent, and this would be the expression on the right-hand side. So using that definition, we could write this as 3. So 3 cubed is equal to 5 over x plus 1. Then you simplify that. So you know that 3 cubed is equal to 27. So you have 27 is equal to 5 over x plus 1. And then we can do cross multiplication. So we can multiply this expression here to eliminate this denominator. Or in other words, we can also multiply both sides by x plus 1. So multiplying both sides by x plus 1, we can eliminate the denominator here. Then we have x plus 1 times 27 is equal to 5. Then our next goal is to distribute 27 to each term inside the parentheses. So we have 27x plus 27 is equal to 5. Then we transpose 27 on the other side because we only want to solve for x. So we want to be able to isolate x. We can do that by subtracting 27 on both sides. That will give us 27x equal to negative 22. Then you can divide 27 on both sides. So therefore x is equal to negative 22 over 27. Now let's consider a different example. We have logarithm of x squared minus 9 base 2 minus logarithm of 2 base 2 is equal to 3. We have difference of logarithms here and the bases are the same. With that, we can relate the logarithm of quotient here. So we can write this in compact form using the quotient rule for logarithm. So this can be written as, or the left-hand side can be written as the logarithm of x squared minus 9 as our numerator divided by 2 base 2 is equal to 3. Again, the logarithm of m over n is equal to the logarithm of m minus the logarithm of n. So we use that property to write this expression in compact form. Then after that, we will use the definition of logarithm to convert this into exponential form. So to convert this in exponential form, let us identify the base. The base is 2 here, the exponent is 3, and the expression on the right-hand side is x squared minus 9 all over 2. So this is just equal to 2 cubed equal to x squared minus 9 over 2. Now 2 cubed is 2 times 2 times 2. That gives us 8. Then let us eliminate the denominator here 2 by multiplying both sides of the equation by 2. So we have 16 equal to x squared minus 9. Then we can add both sides of the equation by 9. 16 plus 9 is 25. So 25 over x squared. Then solve for x. X is equal to plus or minus 25. Now, it is also important to check whether this one satisfies each of the term here. Because we know for logarithm that the expression here has to always be positive and cannot be equal to 0. So if you plug in, so you can check, you can plug in x in here. So if x is, this one should just be x is equal to 5 and not 25. Okay, so x is equal to plus or minus 5. So if you plug in 5 here, 5 squared is 25. Or negative 5 squared is also 25. And 25 minus 9 gives you a positive number. So that gives us the answer, that confirms that the answer are these values here. X is either plus or minus 5. We can also use the one-to-one property of logarithms to solve for logarithmic equation. So for instance, if we are given log of s base b equal to log of t base b, we can then say that s is equal to t. Or if we're given s is equal to t, then we can say that log of s base b is equal to log of t base b. It is also possible that when we use one-to-one property, we may end up with a quadratic function that has multiple solutions. In this case, we want to check each solution to make sure that the argument of the logarithm is positive. And if we find a solution that causes the argument of logarithm to be negative, then that is an extraneous solution. So for any algebraic expressions s and t, and any positive real number b, where b is greater than 1, b is positive and greater than 1, log of s base b is equal to log of t base b, if and only if s is equal to t. Note that when solving an equation involving logarithms, always check to see if the answer is correct or if it is an extraneous solution. So here are the steps that you should follow when solving equation containing logarithms and solving it using the one-to-one property. So first you use rules of logarithms to combine like terms if necessary so that the resulting equation is of this form here, and then use the one-to-one property to set the arguments are equal. Then you could say s is equal to t. And then you solve for the result for the unknown. For example, here, we want to solve for x. To solve for x, we can use the one-to-one property. We have ln of x squared equal to ln of x plus 6. Now, using the one-to-one property, we can just like cancel out the ln. We can say, since this is one-to-one, we can just say x squared is equal to x plus 6. So we then have the equation x squared equal to x plus 6. You can transpose this on the left-hand side. So you can subtract x and minus 6 on the right-hand side, and then you do that also on the left-hand side. That gives you x squared minus x minus 6 equal to 0. Then after that, you can factor this out. So factoring this out gives you x minus 3 times x plus 2 equal to 0. Then since the product is 0, therefore we say that this factor, one of these factor here may be 0. So x plus 3 x minus 3 is equal to 0, or x plus 2 is equal to 0. And then you can solve for x here. From here, if x minus 3 is 0, then x is equal to 3, or if x plus 2 is 0, then x is equal to negative 2. Now, before we conclude that these two are the solutions, we have to go back to the original given and plug in each of these values. We have to make sure that each of these each of these expression here, each of the argument is positive. So if x is 3, x squared is 9, so that's positive. And then x, or 3 plus 6 is also 9. Now if x is negative 2, then we have negative 2 squared. Negative 2 squared is also positive. Now, negative 2 plus 6 is also positive 4. So both of these equations, or both of these values of x, will hold. So x is equal to 3, or x is equal to negative 2. Now, this equation here, let's solve for this equation using the one-to-one property. Now, these are already in compact form or condensed form. So we'll go ahead and say that since the logarithm of 6x minus 4 base 13 is equal to the logarithm of x, or 8 minus 6x base 13, then by one-to-one property, we can say that 6x minus 4 is equal to 8 minus 6x. Then from here we can solve for x. We can isolate x, so we can do that by maybe adding 6x on both sides. So I'll add 6x here. And then that gives me negative 4. 6x plus 6x is negative 12x minus 4 equal to 8. Then I can transpose this 4 here to the other side by adding 4 on both sides. That gives me 12x equal to 12. So therefore, to solve for x, I can just divide 12 on both sides. So 12 over 12 is equal to 1. So x, therefore, is equal to 1. Now, go back and check if that would result to a positive expressions here. So if x is equal to 1, you have 6. 6 minus 4 is 2. So that's okay. Now, if x is equal to 1, you have 8 minus 6. That is still 2. So therefore, the value for x here is 1.